The place is White Sands Missile Range. The occasion, an R&D flight test of the Army's Hawk air defense missile. Time, 1,000 hours. Temperature, 70 degrees. Weather, clear and windless. These were nearly ideal climatic conditions for this successful test firing. But how well would this or any other missile have performed in the frigid atmosphere of the Arctic? The heat and humidity of the jungle, the salt fog and spray at sea, the blowing sand of the desert, the hard, driving rain of the tropics, the hot sun at the equator, or the extreme conditions of outer space. This building at White Sands Missile Range is the headquarters of the Climate Makers, home of the Environmental Testing Laboratory of the Army's Ordnance Mission. Here, practically any known environment can be simulated. To find out what goes on inside, let's follow one of the engineers of the Environmental Test Staff. Today, this man begins a new assignment. He is to plan, supervise, and evaluate the results of a variety of environmental tests of the Army's Hawk missile system. Yes, the project officially begins today, but it really began some time ago in the brain of this environmental engineer. In brief, his job is to determine if the Hawk system can function effectively in any environment it may be used. How can such environments best be simulated in the confines of the laboratory? What specific problems should be looked for? What are the criteria of success or failure? What measuring instruments should be used? These are only a few of the problems. Here in the quiet of this office, pass the crucial minutes of the whole test program. The first plan to go on paper calls for an operational test in a cold environment. Here is spelled out in minute detail the plan of operations, the necessary test specimens, personnel, facilities, instrumentation, outside support, and numerous other requirements. After weeks of careful planning, actual testing begins as Hawk missiles enter the cold chamber. The men, materials, the equipment, the facilities, everything is set to carry out the plan of tests. Conditioning equipment lowers the test chamber temperature to minus 40 degrees Fahrenheit. Instrumentation for measuring and recording test results has been checked out. In the frigid air of the test chamber, the entire system's effectiveness of operation is tested. Components are checked for reaction to the cold environment. Test chamber personnel wear special clothing in accordance with Army Medical Corps' suggested safety requirements. Test objectives are not concerned solely with determining the possibility of catastrophic failures or other obvious breakdowns. More subtle degradations are also closely watched for. Test objectives include a search for slowed down response rates to input signals, lowering of voltages, and loss of power. Such weaknesses are checked for on all missile systems tested, not just the Hawk. In fact, the highly efficient Hawk system is depicted in this film strictly as a typical project of the Environmental Laboratory. The test concluded, specimens are removed from the chamber after it is brought back to normal temperature. Had malfunctions been discovered, various laboratory analyses would follow to determine causes. For example, the increase in viscosity of some hydraulic fluids when subjected to cold temperatures adversely affects the pumping system. Note the molasses in January character of this refrigerated fluid. And here at room temperature is fluid from the same original source. In actual operations, when harmful viscosity changes are discovered, they are investigated and findings reported to the missile designers. Each phase of testing must be independently planned. Next on schedule, a high temperature test. The test specimen enters the environmental laboratory building, headed into the hot chamber. Final adjustments are made on test instrumentation. Controls are set for a chamber temperature of plus 160 degrees Fahrenheit. Again, the specimen is put through all of its operational paces. The principal purposes of this test are to determine the amount of drift in electronic equipment, amount of damage to plastic materials, magnitude of change in the resistance of metals to stress and strain, the tendency of internal combustion engines to overheat, the degree of relative expansion and contraction of fits between parts, and the occurrence of degrading effects on circuit parameters. Suppose a failure did result from differential expansion of metals. This hardness test would be a part of the metallurgical analysis to follow. Next, powdered lucite and a small section of the metal under test are placed in a molding press. Embedded in plastic, the bits of metal are more easily handled and positioned in measuring instruments. Here, the exposed surface of the metal sample is polished. Etching in acid makes grain boundaries of the metal distinguishable when magnified. The specimen is positioned for visual examination in the metallograph, the metallurgist's microscope. The nature of grain distortion may indicate mode of failure. Now the boilers provide steam to produce a relative humidity of 100% in the test chamber. Close examination of the test specimens will be made to spot damage caused by humidity, particularly corrosion of surfaces or dielectric breakdown of materials. A salt fog test comes up next. Objective, to determine how a seacoast environment will affect the Hawk system. Later, in the salt-laden atmosphere of the test chamber, the engineer checks for corrosion. Tests of this type require careful control of atmospheric conditions. Temperature and humidity must be kept within close tolerances. The amount of salt, its relative purity, and degree of acidity must be essentially the same as seawater. Throughout the test, atmospheric samples are taken to ensure control. The samples are analyzed for acidity on a pH meter. If corrosion occurs, a chemical analysis of a sample is performed using the latest tools and techniques of physical chemistry. Here, a corrosion sample is inserted in an X-ray camera for a diffraction study. The corrosion sample is then bombarded with X-rays and its diffractive pattern recorded on film. The diffraction pattern is analyzed to determine the material's lattice structure. The lattice serves as a fingerprint for identifying the atomic structure, one clue to the cause of corrosion. As another tool for analysis, a spectrograph is used to fingerprint all metallic elements in the corrosion sample. An electric arc excites the sample, causing each element present to emit its identifying spectrum. Thus, spectrographic study, X-ray diffraction, and normal chemical analysis provide positive identification of corrosion products and indicate how they were formed. This knowledge is used to determine measures for increasing corrosion resistance. This instrumentation collects data on a dust test of the Hawk system. Inside the test chamber, a fine-grained dust is blown around the missile. The instrumentation measures and controls dust density, temperature, air velocity, and humidity inside the test chamber. Later, the missile will be examined for degrading effects on delicate high-tolerance parts, electrical relays, precision bearings, external protective coatings, hydraulic filters, and delicate surfaces. Here in the environmental laboratory, hydraulic fluids from the missile system are examined for dust contamination. The fluid samples are carefully filtered to trap any dust particles present. The filter is removed for microscopic examination. Under the microscope, dust particles on the filter are counted and measured for size. Particles over a given size can damage finely machined surfaces or precision valves. They may plug hydraulic filters or produce other harmful effects. In a rain chamber, the test specimens are exposed to artificial rain. The rate of fall amounts to 4 inches per hour. Fluorescein dye has been added to the rainwater. This dye, under fluorescent light, indicates points of water penetration inside a test specimen. A simulated altitude test is also programmed. Any altitude up to 70 miles can be simulated. The primary purpose of these tests is to check for leaks from hydraulic systems or other sealed components. All circuits are tested for the presence of arc over in the high vacuum of an altitude chamber. The system is also tested for susceptibility to fungus attack. Here, an electronic component is received in the mycology laboratory. Conceivably, this equipment could be rendered inoperable by fungus, either feeding upon its material or by interfering with mechanical contacts. The mycologist begins preparation of several spore suspensions. The spores, equivalent to seeds of plants, are grown from stock cultures of various species of fungi. On this auger slant, they will produce new spores. The spores are carefully rinsed off the surface of the auger slant and are ready for mixing with spores of other species. Now the mixed spore suspension is ready for use in inoculating the test specimens. In this fungus chamber, temperature and humidity are maintained to provide optimum conditions for fungus growth. Samples are taken from the specimen after it has been disinfected to kill live fungi. Now preparation of slides for the microscope begins. The samples are stained to make the fungi structure identifiable under the microscope. A check for fungus-inflicted damage and type of fungus responsible is made to determine corrective materials or methods of fungus proofing. Solar radiation tests have revealed that external surfaces of missile shipping containers may heat up to more than 175 degrees Fahrenheit, and that internal temperatures may exceed 145 degrees. Absorption of the sun's energy of such magnitudes makes essential testing the reaction of delicate missile components. Even in unfavorable environments, an Army tactical missile system must be able to withstand transporting and rough handling. To determine its ability to do so, a test specimen is subjected to shocks and vibrations at both high and low temperatures. A vital part of all test plans is the establishment of instrumentation needs. And since valid test results depend upon accurate and reliable temperature control and measurement, highly trained specialists disassemble, clean, and reassemble all instrumentation prior to each test. Each instrument system is then calibrated to within plus or minus 1/2 degree Fahrenheit. After completion of tests, the instruments are recalibrated to determine whether accuracy has been maintained throughout. The environmental laboratory also performs pre-firing conditioning tests at missile launch sites. Here, in a typical low-temperature preconditioning test of a Hawk missile, the conditioning unit withdraws from the shroud. The test temperature of minus 40 degrees Fahrenheit has been reached. The shroud is constructed for rapid removal so that the missile will remain at the desired temperature. All test equipment is cleared from the area within 40 seconds after conditioning stops. You are about to see a Hawk missile fired from inside a conditioned balloon. This is an example of the feasibility of engineering special protection against certain environments, instead of modifying the system itself. The balloon is checked to see how well it has met specifications. A comprehensive technical report is the final and only product of the environmental test engineer. This document is for use of the missile developers in correcting any deficiencies discovered. It represents an expenditure of considerable amounts of effort, equipment, and money. But there can be no compromise when dependable weapons for our armed forces are at stake. reason for being of our environmental missile testers is to ensure that no American missile will fail should it ever be needed for defense of the free world, anywhere on the globe, whether in polar regions, in the tropics, on the high seas, in desert zones, in any weather of this world, as well as out of this world.